Okay, let's look at this lesson where we are finding the area between two curves as opposed to what we've done recently, which is the area under a single curve. And what we're going to look at in these cases is stuff like here in numbers 2 and 3, where I give you two graphs and we're looking for the area contained between them instead of something like number 1 here. I forgot to label this function. We'll call that f. Where you just have a single curve. Number 1 is what we've been doing, and what I want to do is we're just going to go through and set up the antiderivatives that would give these areas. One thing to remember when you're finding the area under or between two curves is that these areas are going to be measured with a positive value. We're not going to have negative areas, which we often had with a single curve that was below the x-axis or traveling right to left or something like that. So just keep in mind that these are going to be positive areas. And when we are doing the area between two curves, it turns out that if you have an f of x, g of x situation where you have a top function and a bottom function, your setup for these is going to be the area under the top function. We're going to start from A to B. We'll do the area under f of x. And if all I want is that gray region between the two, we'll do the area under f, which is all of this. But then what I want to do is eliminate that area that is under G. I need to come back and get rid of all of that. So we will subtract out the area that is under G of x. And when you have the same limits of integration as we do here, a to b of f minus a to b of g, you could actually roll that into a single antiderivative, which is how I will typically set these up. F of x minus g of x dx, and don't forget the dx. That is a very important part of the antiderivative. I know you don't do much with it in the actual integration and evaluation, but it is important, so please remember to write it. And so what we ended up here was we did the area of the top curve minus the bottom curve. In number 3, we have another situation where we have a top curve and a bottom curve. Just pay attention when they intersect. A lot of times you can lose track of which one's on top. If you follow the graph of G, that is our upper boundary for this region. So for number 3, we would set this up. It's still the area from A to B, except in number 3, my function G is on top, and then F is on bottom. So we'll do F minus G, and don't forget the dx. And that antiderivative would give you the area of the region on number 3. Let's move on and look at these three. Number 4, if we have a function that is above the x-axis and a function that is below the x-axis, it's still going to set up the same way. The orientation of the graphs, whether their position in relation to the axes, does not affect the setup. We're still going to do a to b of the top function, f of x, minus the bottom function, g of x. And if that confuses you a little bit, what you could do is go into thinking land real quick and just kind of assign some values to these areas and see what it would be. For example, let's say the area under f of x from the x-axis up. Let's say this region right here has an area of, I don't know, we'll just say 7. And then let's say this region down here under g, well, we're below the x-axis, so that region would be like negative something. We'll call it negative 5. Well, if the area under f is 7 and the area under g is negative 5, that is a total area of 12. And so if I did the area under f minus the area under g, you'll see that that does give you the total positive area, and that is what we're looking for. So their position with relation to the x-axis is not going to influence whether we do top minus bottom or something like that. So just remember that if it is an f of x, g of x situation, and we are finding the total area between two curves, always do top minus bottom. Even in number 5 here, where we have both curves below the x-axis, that does not matter. We're still going to set that up. Area from A to B, top function is g of x minus f of x. And if you want to, you could again assign values for those areas just to kind of play with it and see if that makes sense. But it is still top minus bottom. So just remember, anytime you have a top minus bottom situation, it is always going to be the area from A to B of the top function minus the bottom function. And if it is top minus bottom, it will be a dx situation. We're traveling from left to right, and that is a change in x's, which is what the dx stands for. So just remember to keep track of your variables, because as soon as you get comfortable with the dx situations, I'm going to throw something at you like number 6 here, and now my functions are functions of y. They are not functions of x anymore. And when we set these up, you just have to remember that if it's the case where you have a right and a left situation instead of a top and a bottom, this one, we're going to go from a to b. You go from the lower y value to the upper y value, so we'll go from a to b, and in this case it's going to be right minus left, so g of y minus f of y dy. And so if you have a right minus left situation, it will always be right minus left, a to b of the right curve minus a to b of the left curve, and this would be a dy situation. That's one of the things that we're going to have to wrap our heads around for this unit, is that we are not going to be looking exclusively at x's. You're going to have to sometimes reorient yourself to think in terms of y as well. There are two more generic functions that I wanted to look at. Number 7, again, it's two functions of y, and despite the fact that one's on the right side of the y-axis and the other's on the left, that does not affect its setup. It's still going to be the area from a to b of my right curve, f of y, minus my left curve, g of y, and this is a dy problem. Number 8, here we're going back to top and bottom. Going back to top and bottom. Now this one's a little bit unique because my top boundary changes halfway through. And when you have a situation like this where the graphs intersect twice, we're going to actually we have to set up two different integrals. You cannot do this in one big swoop. So we're going to have to first find the region from a to b. So a to b, and now I need to look and see which one's on top. So I'm going to follow my top curve, and f of x is on top from a to b. So f of x minus g of x dx. And then I'm going to add to that the area from b to c. And between b and c, it's the g of x function that's on top. So we'll do g of x minus f of x in this case. It's still top minus bottom, just keep track of which one's on top, especially in cases where the top curve changes in the middle of the overall interval. So there are your generic setups. That's just I'll just remember top minus bottom or right minus left. And I have 3 problems that I want to look at where we are going to find exact areas. And so we're going to find the areas of these 3. This is number 1, the area between the graphs of y equals x squared plus 5 and y equals x cubed. And here I'm giving you the interval 0 to 2. First thing I would do is I would graph these, because you need to know which one's on top and which one's on bottom. So I'm going to graph this real quick. X squared plus 5 is your parabola with a y coordinate of, or I'm sorry, shifted up 5, a y-intercept of 5, and it's going to look like this. So there's x squared plus 5, x cubed, your cubic graph that goes through the origin, and it comes up. Now, I do know that if I go far enough to the right, that x cubed will eventually intersect x squared. And what I want to know is, does it intersect before 2 or does it intersect after 2? So what I'm going to do really quick is I'm just going to plug in 2 to both of these functions. And when x equals 2, this graph, x squared plus 5, 2 squared plus 5 is 9. That's at a y coordinate of 9. And if I plug 2 into y equals x cubed, it's only going to be at a y coordinate of 8. So what that tells me is that on the interval 0 to 2, these 2 graphs do not intersect. This one goes through the point 2, 8. And so now I know that my top curve is always x squared minus 5. My bottom curve is always y equals x cubed. And now I'm ready to set this one up. So it's going to set up the antiderivative. Top curve, x squared plus 5, minus bottom curve, x cubed. This is a dx problem. You need to write the dx. And we're finding the area from 0 all the way up to 2. So we're going from here all the way to 2 right there. 0 to 2. And then we're ready to find the antiderivative. Finding the antiderivative, once we get it set up, everything else is going to be old stuff. The only thing new to this part is the setup. So once I get it set up, I'm going to pause the video and I'll work out the antiderivative very quickly. What you will find is that more often than not, you're going to look at very simple antiderivatives on these problems, mostly power rule. You might run into a u-sub. And if it's a really ugly antiderivative, it will likely be a calculator problem that you can just throw in the calculator after you set it up. So I'm going to pause this. I'm going to work out the answer real quick, and I'll be right back. And there is your answer. If it is a free response question on the AP exam, you are more than welcome to stop as soon as you have all numbers. However, if this is a multiple choice question, you would obviously need to simplify it so you can identify the answer in the 5 options. Alright, so let's look at number 2 here. The area enclosed by y equals x squared and y equals 3x plus 4. Notice on this one, unlike number 1, you are not given an interval to look at. So that means that these curves intersect each other and they enclose a region on their own. Very similar to this problem right here when we set up for number 3. If the graphs intersect, then you're going to have to find those intersection points because those will determine where the antiderivative begins and ends. So I'm going to graph this real quick. Alright, so there's the graph. I can clearly see an enclosed region right here. My top curve is the line, 3x plus 4. My bottom curve is the parabola, so I know my setup is going to be at least this. So it's going to be my top curve, 3x plus 4, minus the bottom curve, which is just x squared. And now what I've got to do is figure out what the points of intersection are. So I need to know what that x coordinate is, and I need to know what this one is right here. Right there. So I'm going to find that intersection. We simply set the two curves equal to each other. So x squared equals 3x plus 4, and we channel our Algebra 1 skills to find those x coordinates. There we go. So we have x coordinates of -1 and 4. And now I have my antiderivative completely set up. Now we simply need to integrate this and evaluate it from -1 to 4. There we go. So it cleans up to 125 over 6. The arithmetic got kind of tricky there towards the end. So there's number 2. And the last one, area enclosed by y squared and y cubed. Now this one, here we're dealing with functions of y, so we're going to graph these real quick. I know y equals x squared is a parabola opening to the right. I'm sorry, x equals y squared is a parabola opening to the right. It's going to look something like this. And then y cubed is going to be a little bit trickier. Y cubed comes in and it looks like this. It's basically going to be your x cubed graphed, only it's the inverse. We're going to flip that and it's going to come around and look like this. Now what we need to do to be 100% sure of is determine if the y cubed graph is on the left side of the parabola, or when we graph it, does it actually come up and do something like that. And so one way we could do that real quick is we could simply plug in. I do know I'm going to have to find their intersection points because I didn't give you any interval to look at, so I'm going to have to find the intersection. So I'm going to start by setting y squared equal to y cubed, and that would be y cubed minus y squared equals 0. You can factor that and solve. You will get y equals 0 and 1. So I know they're going to intersect at y equals 1. And now what I'm trying to figure out is where the y cubed graph is. And so what I could do to figure that out is I could just plug in a y coordinate between 0 and 1. And if I plug in 1/2, so if y is equal to 1/2, I will get x equals 1/2 squared, which is 1/4. And this one, x equals 1/2 cubed, which is 1/8. 1/4, and x coordinate 1/4 is on the right side of 1/8. So that tells me that my y cubed graph is going to come up and it will be on the left side. Ooh, it's going to be tough to graph. Left side, whatever. Okay, that's crap. But it's going to look something like that. It's on the left side. And now I can see that this region right here is what we're looking for. And the question of whether we do a top minus bottom or right minus left, this is a unique problem where you can do one or the other. I would stick with right minus left because my functions are already in terms of y. So when I'm looking at this, I'm going to set up and I'm going to do the right curve, which was the parabola, y squared, minus the left curve, which is the cubic function, y cubed. This is a dy problem, and I'm going to measure this area from y coordinates of 0 up to 1. And once it's set up, we have a very easy antiderivative to finish. Simple power rule and evaluation, and then we will have our answer. And there it is. So the integration was pretty simple, and I kind of told you that at the beginning. Usually these have fairly straightforward antiderivative techniques and evaluation. But anyway, so there you go, and we got a small answer here of 1/12, which kind of makes sense because it was just that little bitty sliver of area trapped between them. So sometimes you can kind of tell if your answer is in the reasonable ballpark for the question. So there we go. We will discuss this further in class. I'm tired of talking.